All right, how's everybody doing? All right. So, as always, remember the seating survey, Section 2, ILC 118. Upcoming deadlines, Wednesday, tomorrow, are the content videos. There are 5 of them this time. The last couple got put up kind of late this weekend, but they're fortunately relatively short, so hopefully it shouldn't be too much of a problem to get through those. The homework on Friday has 3 parts. There was a mistake in last week's where I had, when I changed the dates due to the rescheduling of things, it changed what times they were due. We are back to the original times now of the 5 o'clock. And guided inquiry activity number 3 is now available on Blackboard, and it will be due a week from today at 5. And so you should start thinking about scheduling when you and your group are going to be doing that work. You have covered already the material that is necessary to be able to do this. It's primarily about first order kinetics and looking at it in relation to radioactive decay and how geochemists use that information to date minerals and figure out how old the minerals, how long ago the minerals were formed initially. Do we have any logistical things to talk about before we get into content? Okay, so not surprisingly, we have a bunch of questions on kinetics. So the bulk of them are in kinetic mechanisms, so we will try to do all of those together. I'm going to try to go through these kind of in the order that the videos were presenting the information in first. So the first question is on collision theory and is about the frequency factor and in particular what is meant by the right orientation with it. So the idea of in collision theory is that we're able to find an expression for the rate coefficient that is known as the Arrhenius equation. I may be misspelling that. So, oh, no, I'm not, nope, that's not it at all. Let's try this again. Negative EA over RT. Okay. What we have here is an expression that encapsulates 2 pieces of information. This part of it tells you what fraction of the collisions have an energy in excess of the activation energy. So you may remember that we talked about the kinetic energy distribution at a given temperature as having some spread. So this is a kinetic energy. This is, no, this is not kinetic energy. This is kinetic energy. This is the fraction of the collisions. And this curve is set at a given temperature. At a different temperature, you will have a different curve. So something looks like that. So I picked these because blue is generally thought of as being colder, red is generally thought of as being warmer. So this corresponds to a cold temperature, the red corresponds to a hotter temperature. And then there is some threshold energy, which we are calling EA, for the reaction to happen. And at different temperatures, we have a different fraction of the molecules, or a different fraction of the collisions that have an energy in excess of that threshold. So this part of the Arrhenius equation is telling you that fraction. This part of the Arrhenius equation is basically telling you everything else about about the collision, how effectively it can happen. And the example that I used in this case was orientation. So A here is called the frequency factor. And the idea is, suppose you have some kind of reaction with some molecule, and I'm just going to draw the molecules here as blobs. They come together and collide, but suppose that only one portion of the molecule is sort of the active region, is the place where the collision has to happen in order for the reaction to successfully proceed on to products. So if it hits here, it's not going to react. If it hits here, it's not going to react. If it hits here, it will react. Okay. So that is the kind of information that is encapsulated in this constant A, the frequency factor. If there are very, very few mutual orientations for the collision that can lead to a reaction, then A is going to be very small. If almost any orientation will work, mutual orientation will work, then A will be very large. So if you imagine, for example, a reaction where you have, let's say, an iodine atom coming and colliding with another iodine atom, each of these atoms is pretty much spherically symmetric. So, and certainly the electrons can reorient themselves with almost no problem. So if the reaction is these two things coming together and colliding to make an I2 molecule, then that is going to have almost no orientation dependence at all, and so your frequency factor is going to be large. If instead we have some very large molecule, let's say this right here is propionic acid. It's an organic compound that you will learn about in organic chemistry. And a lot of reactions happen by coming in on the back side of this carbon that has the double bond to the oxygen. Okay? You don't need to worry about the details of that. You'll learn that in organic chemistry. But if you imagine this kind of reaction happening in the gas phase, that's a pretty small target compared to the molecule as a whole. And so whatever this reaction is, even if what's coming in there is this same iodine atom that's coming into to the backside of this carbon, your frequency factor is going to be tiny because there's not a very big target that's going to be successful in this case. Now, you are not in any way going to be expected to look at a molecule and predict what is numerically the frequency factor, because there's a lot more that goes into it than just orientation. The most you would be asked to do would be to compare two different reactions that are similar in ways other than the sort of mutual orientations that are going to work, and then talk about which one would have a larger or a smaller frequency factor. That's the most you'd be asked to do on that kind of thing. Any further clarifications on the frequency factor, the Arrhenius equation in general, collision theory in general, before we move on to reaction mechanisms? So a question in the chat, example on what we would be asked. So you could imagine me asking, okay, we have I explained that the reaction to one of these kinds of compounds would have has to come into this region. And then have you compare maybe this molecule to a similar molecule that has more carbons. And then, no, those should be hydrogens coming off. And then extra hydrogens on the rest there. So I might ask you between these two, which one would you expect to have a larger frequency factor? And so since this one, as a term, in terms of the proportion of the molecule, this is a smaller target. I mean, it's physically the same size target, but compared to the molecule as a whole, it's a smaller fraction of the molecule. So this one would have a smaller frequency factor. This one would have a larger frequency factor. Yes?
So is the K in this equation, and this might be kind of a bad question, but is it the same as like the rate coefficient that we were?
Yes. So the question is, for those in the chat, is the K that we're talking about here the rate coefficient in the rate law? And the answer is yes. So it turns out that this Arrhenius equation works very well for whatever K you're dealing with for an elementary reaction. Whether it's a first order, second order, or even third order rate coefficient, it still follows the Arrhenius equation. But you know that the K's in those three cases have different units. So that means that the A's will have different units. Okay? Yes?
Do you usually ask to find something else in the equation, or are you asked to find K?
So, you might be asked to find K. You might be given Ks at different temperatures and be asked to find the activation energy.
Would that be the little e?
That's the EA. The little e is the base of the natural logarithm, the constant 2.7 I don't remember it. I always have to look it up. So the EA is the activation energy. Okay. Any other? Yes?
Can you explain what each of the letters mean in the equation?
What do each of the letters mean in the equation? Okay, so K is the rate coefficient. A is the frequency factor that we were just discussing. The lowercase e is the base of the natural logarithm. EA is the activation energy. R is the gas constant, from the ideal gas law, and T is the temperature in Kelvin. Okay. Okay. Anything else on any part of collision theory before we move on to mechanisms? Okay, so let's see. Collision theory, I'm sorry, kinetics, kinetic mechanisms. So how do you know if a reaction is single or multi-step? So there are a couple of different ways to approach that question. One is that in a particular problem you might be told which way it is. If you are looking at experimental data, if the rate law for the reaction does not match the molecularity of the reaction as written, then it has to be multi-step. Let me state that again, and we want to make sure we understand each of the concepts that we're talking about there. If the experimental rate law does not match the molecularity of the reaction, then the reaction must be multi-step. So one of the things that we developed in looking at collision theory is that when you have an elementary reaction, then if we have a reaction that is something like 2A plus B goes to products, then because it's an elementary reaction, we can write down the rate law for this step as concentration of A squared times concentration of B, and I forgot the rate coefficient out in front. So in an elementary reaction, and only necessarily in an elementary reaction, the coefficients, the stoichiometric coefficients, are the reaction orders. So if you write down the reaction, we'll do a different one. We'll say it's A plus 2B goes to products. And if you experimentally measure the rate law and find that the rate law does not match the molecularity of the reaction, so that here, if it were an elementary reaction, we would expect the B to be squared here. If experimentally the rate law that you get does not match the stoichiometric coefficients, then the reaction must be multi-step. Okay. Now, if you experimentally measure it, and you find that it does match, if you experimentally measure it and find that it does match what you would predict from the stoichiometry of the reaction, that does not prove that it is a single step. That does not prove that it is an elementary reaction. Because you could have a reaction mechanism that is multi-step that happens to produce the same rate law. Yes?
Does it mean the elementary reaction means that it only has one step?
That is what we mean by an elementary reaction. What we mean by an elementary reaction is that it proceeds through a single collision, through a single step. When we say a reaction mechanism, what we mean is a collection of elementary steps, single collision reactions, that together produce the overall reaction that we're trying to understand. Okay. Okay. So, how do we know if a reaction is single or multi-step? Well, in the context of a problem, you could be told it's single step, you could be told it's multi-step. In the context of a problem, you could be given a rate law or given data to determine a rate law, and then from that you could determine it must be multi-step, or it might be single step but might not, we can't tell. If you are given a proposed reaction mechanism, then by definition, each of the steps in that mechanism is understood to be an elementary step. Because that's what we mean by a mechanism. We are listing elementary steps. So those are the contexts in which you would be able to determine if a reaction is single or multi-step. Clarifications on that? Okay. How do you know how to order your steps? So, honestly, I think this question was asking something slightly different from what it sounds like. When you write down a reaction mechanism, there isn't really an order to it. It's just, these are the things that are happening. So if we have A plus B goes to C, we have then C plus B goes to D, D plus A goes to, let's say D plus A goes to our product E plus A. Now, all of these things are happening simultaneously. There is no order to it. Now, it is true that C here is an intermediate that gets used up in making D. And so you can't really have this step happen before this step happens. But in a reaction mechanism, you can always have a step here, for example, this third one, is it has some A that's involved, and that A, after it does this, could later go back and do the first step. So there isn't really an order to it. But I think what this question is asking about is not so much about ordering the steps, but how do you know which one is rate determining? How do you know which step is the one that you use to say this is determining the overall order? So there are a couple of different ways to do that. So the first thing I want to do is take this kind of bizarrish mechanism that I have here and figure out what the overall reaction is. So it looks like we've got 2A on the left, 1A on the right, so one of those is going to cancel, so we're going to have an A here. We have 2B on the left plus 2B. We have a C, but that was produced here. We have a D, but that was produced here. So it's going to be A plus 2B is going to make the C gets used up, the D gets used up, makes an E. Okay, so that's our overall reaction that we have. There are two ways to go about determining which of the steps that we have here. And so I'm going to label these K1, K2, K3 for the different rate coefficients that we have. One way is to say one of these steps is significantly slower than all of the others. And so that step is rate determining and thereby causes us to use that as the overall rate. Because the idea is that in a sequence of reactions, the overall sequence can only go as fast as the slowest step. And so if K1 is the rate determining step, meaning that it is slower than K2 and K3 by a significant amount, then every time K1 happens, very, very rapidly K2 and K3 happen. And so those don't have any effect on the overall rate. And so in that case, if this is rate determining, then we can write the overall rate of the total reaction as K1, concentration of A, concentration of B. The other way you could go with this is to say, well, you know what? E is the product. So the reaction is done when E is produced. So our rate overall is going to be K3, concentration of D, concentration of A. But the problem we have with this formulation of it is that D is an intermediate. It is something that is produced over the course of the reaction mechanism and is then destroyed over the course of the reaction mechanism. And as a result, it's not something that we can control by changing our starting conditions. We can't have an initial concentration of D because it shows up and then goes away very quickly. And so for our overall reaction rate, we then would have to use the steady state approximation or pre-equilibrium approximation or something like that in order to algebraically find a way to get rid of D and put D in terms of K1, K2, concentration of A, concentration of B. And so in the reaction mechanism video, I went through those two kinds of approximations I was describing, steady state and pre-equilibrium approximations, and you would do that. Now, I do not expect you to be able to look at a reaction mechanism and be able to somehow intuit which step is rate determining, or whether you would need to use the steady state approximation or the versus the pre-equilibrium approximation. I don't expect you to be able to just look at it and know that, because there's a lot of chemical intuition that goes into those kinds of determinations. You would have to be told things like which one is rate determining, or at least be told what are the rate constants that you're dealing with. So if this has a rate constant of 10, and this has a rate constant of 20,000, and this has a rate constant of 80,000, then this is the slowest one. So that has to be rate determining. Okay. So, any questions on those ideas of what information you start with in order to determine the overall reaction rate? All right. So let's see here. How do you calculate the rate of destruction in a multi-step reaction, and what is physically going on when that happens? So I've seen several Piazza questions that are seeming to get a little bit hung up on rate of X, you know, rate of destruction, rate of consumption, rate of something. These are all just rates. There's nothing special about any of them. I would, if I hear the term rate of destruction, basically all that tells me is we must be talking about the rate as measured by looking at the disappearance of a reactant. That's really the only thing I can take from the word destruction here. So I would not worry about there being different rules for rate of X for whatever X is. There really isn't. It's just what can I understand from the word about what we're talking about. So it would make sense in this case to talk about the rate of destruction, the rate of destruction of A. It would not make much sense to talk about the rate of destruction of E, right? Because that's a product, so that's not being destroyed, it's being formed. Now, maybe, okay, now that I'm thinking about this, maybe this is referring to the steady state approximation. So let me talk through that for just a moment. The idea of the steady state approximation is that when you have an intermediate, like in this case we have C as an intermediate and D as an intermediate, one of the approximations we can make is that the concentration of the intermediate doesn't really change much over the course of the reaction because it's being made and it's also being destroyed. So it's probably going to be, it's going to reach some level and then it's pretty much going to stay there until the reaction's done. And so I do remember saying in the video that in that context, the rate of production of the intermediate is going to equal the rate of destruction of the intermediate. So let's look at how we would actually do that and apply it to this particular example. Okay, so let's suppose that we're not told the rate constants up here, and so we don't think that we can just say that this is rate determining, and instead we have to say overall we should be looking at the production of E as the final product that we have. So the first thing to do is to write down the rates of the individual reactions that we're dealing with here. So remember, when we write down a mechanism, we are implicitly making the assumption that each of these steps are elementary reactions. And so you should be able to write down the rate of that reaction just from the stoichiometric coefficients. So in this case, the first reaction rate, R1, is going to be K1, concentration of A, concentration of B. So somebody tell me R2. What is reaction rate 2? Yes. Correct. K2, concentration of C, concentration of B. Somebody tell me R3. I missed the 2 there. Yes.
K3, concentration of D, concentration of A.
Correct. K3, concentration of D, concentration of A. All right. So we now have those 3 steps. We are looking at our overall rate and we see D is in there and we don't want it there, right? So we are going to make the steady state approximation for D, saying that its rate of production equals its rate of destruction. So its rate of production is step 2, because we are making D there. So our rate of production is K2, concentration C, concentration B. Its rate of destruction is step 3, because the D is going away. So that is going to be K3, concentration of D, concentration of A. All right. Now I'm going to label this steady state, because what we are doing is we are saying that the concentration of D we are assuming is going to be steady, is not going to be changing. That's the point of saying its rate of production and rate of destruction is the same. And now we can solve this equation we just wrote for that steady state concentration. Concentration of D, steady state, equals K2 concentration C concentration B over K3 concentration A. Right? And that then can get plugged into our overall rate that we have. So our R overall now becomes K3 times K2 concentration C concentration B over K3 concentration A times concentration A here. And we have some things that cancel, so this simplifies. K3's cancel, concentration of A cancels, and so we now have K2 concentration C concentration B. Okay. Now let's see if we can do the same thing for C, because C is also an intermediate. All right? We're trying to get rid of all the intermediates in the course of the analysis we're doing. So, what is the rate of production of C? Let's bring that over here. R1. So the rate of production of C is K1 times concentration A, concentration B. All right. What is the rate of destruction of C? R2. It's going to be K2, concentration C, concentration B. And C is the thing we are doing as steady state. So we now solve this for concentration of C. And concentration of B is going to cancel, right? So K1, concentration A over K2. All right, so now we go back to our rate overall that we have here and plug in for concentration of C. So we have now K2 times K1 concentration A over K2 times concentration B. K2's cancel, and we end up with K1 concentration A, concentration B. And now we have a rate law that is determined entirely in terms of reactants that we arrived at by using the steady state approximation. General idea making some sense? Okay, there's some chat questions here. Why isn't there 2A on the reactant side of the cumulative equation? The two B's came from the two separate B's in the parts, but there are also two A's on the reactant side. That's correct, but there's also an A on the product side, so that gets canceled out. Looks like that's been, yeah, that's already answered, so okay. 2A plus D equals EA. Yeah, A is used in the first step. How's it present for the last step? Okay, looks like they're following. Okay, any other clarifying questions on this general set of topics? Okay. Can you walk through and just tell where you get each one from? To get the overall reaction? Okay, sure. Let me do it on a clean sheet of paper since there's a lot of writing on there already. So we have A plus B goes to C, C plus B goes to D, D plus A goes to E plus A. So adding it together, we have AA for 2A plus 2B plus C plus D goes to, we have an A plus C plus D plus E. We have a D on both sides. We have a C on both sides. And we have an A here and two A's there, so the two cancels out. So we end up with A plus 2B goes to E. Okay. All right. All right. Moving on. Rate of total equilibrium reaction. In kinetic mechanism video, we got 3R overall from the other rates. How is this done? I may have to call up that video and try to find that bit. Let's go, nope. Oh, I don't want to do the version with the quizzes right here. All right. Okay, so let's see. This was an example, so it might be this one, which we had two equilibria that we're looking at. And so the question is asking 3R overall from the other rates. Okay, so the basic idea here is that we are told that this last step in the mechanism is the rate determining step. Because these are equilibria, they have a forward rate and a reverse rate. So that's why we have the forward rate here. So notice that this is two of these, so that's why this is squared. The reverse rate is going to be one of these, 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 one of these. Yes? I don't have these PCs thing up on the screen. Thank you. Apologize. Trying to navigate what the chat is seeing. Oh, and the chat can't see that either because I haven't screen shared, so everybody's going to be confused. Here we go. Okay, hopefully everybody can see this now. All right. So in this particular example, in the content video, we had this overall reaction, and we proposed this 5-step mechanism. It's 5 steps because each of the first 2 steps are reversible. Okay. We have a forward reaction and a backwards reaction, forwards reaction, backwards reaction, and then final reaction that happens. And we are told that this is the rate determining step. So our overall reaction rate is going to be this, but unfortunately both of these are both of these are intermediates, so we need to get rid of both of them. So in the pre-equilibrium approximation, what we do is we say when we have an equilibrium, that equilibrium gets established, meaning that the forward reaction and the reverse reaction are happening at equal rates. So this is similar to when we were talking about vapor pressure. We have rate of evaporation and rate of condensation. And so dynamic equilibrium is that both of those are happening at the same rate. Because these are now elementary steps in this proposed mechanism, we can write the rate of the forward reaction. So it's going to be K1 times this squared, because there are 2 of them. The reverse reaction is going to be K minus 1 times concentration of each of these 3 components, and so on. And then what we do is we say that the pre-equilibrium approximation is this rate equals that rate, which is what we see here. We have our intermediate, which we can solve for. We say this rate equals that rate, which is what we say here. We solve for the intermediate, and then we plug them in, and we are able to get the overall reaction rate by plugging in for both of these values that we just found, canceling, and we find a result where there is only the reactants that are listed. So it's relatively straightforward algebra once you know what you're doing in terms of assigning the rates of the steps and which ones you are assigning to be equal to each other, so that you can then solve for the things you're trying to get rid of and plug it into the overall rate. That's the general strategy to be using. Any questions on that general approach? The chat. Okay. All right. There was a question about the question about the solution phase kinetics video. So in the solution phase kinetics video, I introduced this new notation of this right here. The idea is that in solution, if we have A plus B goes to products, what happens is that we have our solvent molecules that are jostling around. We have a solute molecule, another solute molecule of the other type that are separated from each other. And they are bouncing around. And then occasionally they will run into each other to form what is called an encounter complex, where you have this, so that there is essentially a solvent cage that is holding the A and the B in close proximity to each other. That is what we mean by this notation here. The A and the B have not reacted yet. So they're separated by the little dots, meaning there's a little bit of distance between them. But they are held in close proximity to each other by this solvent cage, which is what the parentheses are referring to here. And so the mechanism we write for this is A plus B goes to this encounter complex. This is a reversible thing because these two can then diffuse apart from each other. And so we have a rate coefficient here of KD, and we have a rate coefficient here of K minus D. But then the splitting apart, the diffusing apart, is competing with another step, which we call KR, which is the reaction of the two that goes on to products. So the specific question that was being asked here was trying to understand the difference in the notation between this and then just the concentrations multiplied by each other. They are very different things. This is the concentration of A times the concentration of B. This is a different component. This is the encounter complex that is being held together by the solvent cage. The point of the video, the point of this analysis, is that we developed collision theory for the gas phase, where we could essentially catalog the amount of energy that's available for the reaction based upon the kinetic energy of the collisions that the molecules have with each other when they run into each other. But pretty clearly, that's not what's going on in solution, because the molecules are constantly in contact with each other, exchanging energy with each other, and so you constantly have this adjustment of energies. Additionally, in the gas phase, two molecules that come together in the wrong orientation will hit each other and bounce off. Whereas in solution phase, they will diffuse to each other by sort of a random walk kind of thing. There's actually the mathematics behind this. They actually call it a drunkard's walk as the molecules diffuse towards each other and run into each other. Then they get stuck in this solvent cage for a little while, and they can jostle around, bounce around, reorient, and change their orientation in a way so that perhaps in one of those multiple encounters while they're still stuck in that solvent cage, that can then go on to cause a reaction to happen. So the process, the physical picture of what's happening in solution is extremely different from the physical picture of what's going on in the gas phase. But what we did in that video was go through analyzing this mechanism in terms of rate determining steps, where this is a rate determining step here for the reaction that's going on. And what we found was that mathematically, the results that we get are exactly the results we would expect if it were happening in the gas phase, with one exception. I'll get to that exception in a second. But so the point of that video was to illustrate that even though the physical picture of what's going on in solution is utterly different from what's going on in the gas phase, all of the math that we went through for gas phase reactions applies to solution phase reactions. That was the point. I said with one exception. That one exception is when a KR is not the rate limiting step. If KR is really, really fast, then every time A plus B happens and they form the encounter complex, it goes on to products. That means that the KD step is the rate limiting step. And so as long as KR is big enough, it doesn't matter what KR is. There is a maximum speed at which reactions can happen in solution, and that's determined by KD. That is known as a diffusion-controlled reaction, and it's a limit. It's a speed limit for these reactions. And so in water, at room temperature, KD is usually in the about 10 to the 9th to 10 to the 10th kind of range in units of per molar per second. And so there are a couple of reactions in solution that can happen faster than that, but that they happen by a very, very different mechanism, which is kind of fun, but it would be distracting at this point, so I'm not going to go into those. Yes?
Does the A and with the dot dot dot, B, does that have a numerical value?
Does it have a numerical value? That is the A dot 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 B in parentheses, that is considered to be a species, just like A is a species and B is a species. This is a notation that we use to talk about this picture right here.
You
Okay.
would have to multiply by.
No.
I don't know why they're negative.
Okay, that's just a, so this is a subscript of negative d, of minus d. That is a notation that we use in kinetics to indicate that this is the reverse of the reaction for Kd. So it's not actually saying subtract d or something like that, or even take the negative of the Kd. It's that, it's a notation saying Kd and K minus d are related because they are the two halves of the dynamic equilibrium we're dealing with. Does that make sense? Okay. And the chat asked the same question. Okay. Excellent. Okay. All right, are we okay with solution phase kinetics at the moment? All right. All right, last question here was about spectroscopy. I know there were some questions in Newton about that, and I really regret not having made a content video on spectroscopy. I didn't realize that there were going to be as many Newton questions as there were on it, and that, honestly, spectroscopy is such an important tool in chemistry, I really should have included that as one. I'm going to do a brief overview of that right now. I may add a video about that at some point in the near future because it is really pretty powerful. So the idea is that if we look at how much light is absorbed by a sample as a function of wavelength in nanometers, you're going to get some kind of plot like this. Each wavelength of light corresponds to a different energy. Okay? You may remember back from Chem 111 talking about the hydrogen atom and talking about it can absorb a photon of light to go from a low energy level to a high energy level. Or if you're already at a high energy level, it can emit a photon of light to go from that high energy level to a low energy level. That's spectroscopy. And so what you do is you plot how much light gets absorbed by a sample as a function of wavelength. And there are going to be peaks here that correspond to a transition between different energy levels in the molecule that you're dealing with. In solution, these peaks tend to be very broad. In the gas phase, they tend to be individual lines that's going to happen. We're not going to get into why that is here in this class. The thing that is important about spectroscopy from the perspective of kinetics is that there's a connection between concentration of your species. I shouldn't use A because I'm using A for absorbance there. We'll call this B. If we take the concentration times the path length, meaning how long what's the distance the light is traveling through the sample, and we multiply it by something called epsilon, which is called the extinction coefficient. That equals our absorbance. Now, this extinction coefficient is going to have a different value at each wavelength that you have. So very often, you will want to pick the wavelength where epsilon is the biggest, because that means you now have the best the lowest noise, the least uncertainty in your determination of the absorbance value, because it's absorbing a lot of light. But if you're trying to think about what's going on with this equation, think about having having a glass of water and putting 1 drop of food coloring in it. You stir it around and you have a pale color, and that pale color is there because the food dye is absorbing some wavelengths of light, and it's absorbing some wavelengths of light more than it's absorbing other wavelengths of light, which is why there are these differences in the spectrum. If you put a second drop of food coloring into the water, it gets darker. You have more absorption of light, and now the spectrum is now bigger. Okay, so what we're able to do is use the amount of absorption that happens to determine concentration. And this is particularly convenient for kinetics, because what we care about in kinetics very often is concentration as a function of time. So if we put our sample that is reacting into a spectrometer and hit go and measure just one wavelength as a function of time, you're going to get absorbance as a function of time, and then you just have to divide by epsilon on your path length to get concentration. So it's really convenient. And so you've looked at some examples where you're doing this kind of thing and you've got like 10 data points, you've got something like this, and you draw a curve through it. Well, if you're doing this in a spectrometer, if you're doing this for research, then you can easily get hundreds or thousands of data points just by pressing go, and you get the full curve of data that's coming out from it. So that is why spectroscopy is really, really powerful in chemistry in general and for kinetics specifically. Okay. So the specific question that was asked on Piazza is, it's always mentioned in nanometers, but the actual wavelength in nanometers is never used. That's because you are given the epsilon at a particular wavelength, and you're making the absorption measurement at that same wavelength. And so it's identifying what the wavelength is. But yes, you're right. You don't have to do any conversions to some different wavelength in these calculations, because there's not a good way to do that. So all it's doing is acknowledging the fact that when you make these measurements, you're doing it at just one color of light, at one wavelength of light. And that's the list of muddiest points that I had, and we still have about 15 minutes left in class. I will happily answer any questions anybody has. Yes? Yes. Excellent question. So for the people in the chat, the question was for the encounter complex in solution phase chemistry, the parentheses A ... B close parentheses, are there ever cases where you have more than 2 in your encounter complex? It certainly can happen. It's not very common for that to happen, because so in the, I think it was the activation energy video for the gas phase, I talked about an example where a termolecular reaction really had to happen when you have 2 molecules that come together to form a dimer of the 2, but it has too much energy for it to stay together, and it would just pop back apart again. So you need that third collision partner in order to carry away the excess energy to allow the product to stay there. And so in gas phase chemistry, we see termolecular reactions not ridiculously commonly, but commonly enough that it's worth knowing about them. In solution phase chemistry, we don't have that same need, because the molecules are all in constant contact with the solvent molecules that are around it, and so any excess energy that you would have is automatically going to get carried away. And so you don't see it very often, because the reason that these rare events are actually important in the gas phase is not true in solution phase as much. So, I mean, yes, it can happen, but because three-body interactions are just statistically rare to happen, you don't see them very often, and there aren't very many reactions that actually depend on it. And conceptually, yes, it can happen. Yeah.
I have an example problem on these. We're going to work out.
Work out an example problem. Sure, happy to. So let me get a fresh sheet of paper and hit me with it.
It has to do with the absorbance measures and not do generally. And there's like two different compounds and one was added to it.
Okay.
And how would you set those up? How would you set it up?
I'm not sure I'm understanding what the problem is asking if you have it.
Trying to find the extinction coefficient for a second compound that's added.
Oh, so you're given measured absorbance. So you have two different compounds that are absorbing at the same wavelength, I think. And you have a measurement on a mixture, and then you add some of one of the compounds and see how much it changes by? Something like that? Okay. Yeah, I can do that. All right, so here's the idea. If you have a sample with one solute and another solute in it at the same time, then the total absorption that you get is going to be the sum of the absorption from the blue and the absorption from the green. Now, they're being measured at the same wavelength of light. By blue and green, I'm just referring to the two colors that I showed here, not saying we're using blue light and using green light. That was an unfortunate choice on my part. Okay, so the idea here is that in this mixture, you can't tell how much of it is coming from B and how much of it is coming from G. But then what you do is you take one of them and you add a known amount of that one. So we are now going to add, say, more green, okay? Add some more of that. And we now have, we now have a new absorption measurement that we made, which is still going to be AB plus AG, but this AG is a new amount, AG prime, okay? We know how much we added, so we will have concentration green new that we added. If we subtract these two, A2 minus A1, we get how much the absorption changed just due to this green amount, right? So this is going to be times our epsilon for the green times the path length. So what I have here on the left is if we only had the concentration of the green stuff that we added, then its absorption would be the epsilon for the green times the path length. And if we look at the difference between these two, A2 minus A1, that tells us how much of the absorption is due to the amount that we just added. So the left-hand side and the right-hand side have to be equal to each other. You're given that information, you're given that information, you're given that information, so you find epsilon G just by algebra. Now that you have epsilon G, you can then use that in this equation. Are you also given an experiment where you add in more of the blue? Yeah? I'll bet you are in order to be able to do the experiment. to be able to get the information you need. And so what you do at that point then would be to find the epsilon b by exactly the same mechanism, by exactly the same procedure. If you had an A3 that was either some stuff added to this one or some stuff added to this one, you would find epsilon b the same way. And then so up here at this point, you know that this is going to be your epsilon b times your path length, which is the same, times your concentration of the blue stuff, plus epsilon g, same path length, concentration of the green stuff. And so if you have both of those two pieces of information and you're given this, you still need one more piece of information to be able to figure out those two, and I don't know what other information you're given. But this is sort of the way that you would go about it, is to try to identify what information do I know, think about absorptions, just they add, and each one of them is in this form, a concentration times an epsilon times the path length. And the epsilon is a feature of the species you're dealing with and a function of the wavelength. And if you're not changing the wavelength, then it's the species, the concentration that you've got. Does that give you enough to get you moving in the right direction? Okay. Okay. What else can we talk about? All right, well, we can call it quits for the day then. So in terms of what I'm going to be getting out to you guys soon, my first priority right now is to get myself a little bit ahead on the videos so that I have some content videos ready early for you for next week. Once I have that done, I'm going to be doing two things. One of them is to put together an example kinetics spreadsheet problem that I have and an explanation video for it. I discussed this in the last couple of class periods. If you want a good explanation of it, take a look at the timestamp that's listed for yesterday's class. I talk about a couple of different things that we could do with that. So I'm going to be trying to get that together so that it will give you some practice working on some of these kinds of problems for in exam style contexts. I'm also going to be starting to work on catching up on the on some grading finally, which I know you all have been very patient with me on it, which I appreciate very much. Thank you very much. Take advantage of my office hours.